Lecture 12 covers Section 3.11. At the end of today's lecture, you should be able to understand the concepts of internal energy, enthalpy, and specific heats of ideal gases under our ideal gas law framework. For us to talk about internal energy and our constant volume specific heat, we have to recall that our internal energy of an ideal gas is determined from two independent properties, such as temperature, pressure, or specific volume. For low to medium density gases, our internal energy depends primarily on temperature and less on pressure. That is, we can say our internal energy is a function of temperature. U is equal to U of T. If we recall the ideal gas law, and if we state that U is equal to U of T, this implies that our internal energy is independent of our pressure and specific volume. Now, recall that our constant volume specific heat, C sub V, is defined as our change of internal energy per our change of temperature. Now, we stated that our constant volume specific heat is independent of our volume, or our specific volume. That is, our constant volume specific heat was a material property. Thus, we say CV naught is equal to du dt for an ideal gas. And this definition does not vary from what we've defined previously. The only difference is the zero, or naught, next to our V within our subscript. This indicates that it's used for an ideal gas. Now that we've defined our constant volume specific heat for an ideal gas, let's look at our constant pressure specific heat for an ideal gas. Now, we're going to recall the definition of enthalpy in our previous framework. Enthalpy is equal to internal energy plus our pressure times our specific volume. If we recall from the ideal gas law, our pressure times our specific volume was simply equal to our gas constant times our temperature. Or we could say H is equal to U plus RT. And once again, we see that our enthalpy is a strong function of temperature. That is, our internal energy is a function of temperature, and RT is also a function of temperature. Recall that our constant pressure specific heat is our change of enthalpy per our change of temperature, and it was independent of pressure, also the path we took. Therefore, we define Cp naught as dH dt, which is our constant pressure specific heat of an ideal gas. Now, our constant volume and constant pressure specific heats are given in table A5. Cv naught and Cp naught are related through our definition of enthalpy of an ideal gas. Now, H is equal to U plus PV, which is also equal to U plus RT. If we differentiate this equation, we have our change of enthalpy is equal to the change of internal energy plus the change of RT. And this is equal to our change of internal energy plus RdT plus TdR. Our gas constant is constant, and dH and du can be expressed in terms of our constant pressure and constant volume specific heats respectively. Therefore, dH is equal to du plus RdT, which can be expressed as Cp naught dt, is equal to Cv naught dt plus RdT. If we divide out by dt and solve for R, we see that R is equal to our constant pressure minus our constant volume specific heat. That is, our gas constant is a constant based upon our two material properties, our constant pressure and our constant volume specific heats for ideal gases. Note table A5 has our constant pressure and constant volume specific heats given at standard temperature and standard pressure. We note that these are valid for elevated pressures. If we go to table A6, we see our constant pressure specific heat given as a function of temperature. That is, Cp naught is equal to C naught plus C1 theta plus C2 theta squared plus C3 theta cubed, where C naught, C1, C2, and C3 are constants given, and theta is our temperature in Kelvin divided by 1000. Now note, if the gas published within has C1 is equal to C2 is equal to C3 is equal to 0, our specific heat is a constant and does not vary as a function of temperature. Lastly, our enthalpy is tabulated as a function of temperature in table A8. Now, when we're evaluating the change of enthalpy between two states, there are multiple ways to evaluate our constant pressure specific heat for an ideal gas, and these are in order of worst to best. If dt is small and near 25 degrees centigrade, we'll use table A5. Since table A5 reports our constant pressure specific heat at 25 degrees centigrade, we might introduce error if our temperature is elevated above 25 degrees centigrade, if and only if our constant pressure specific heat is a function of temperature. If our change of temperature is small and between 250 and 1200 Kelvin, we're going to use table A6, where we can either use our average temperature to evaluate our constant pressure specific heat, or we can take an average constant pressure specific heat. if our change in temperature is large, we're going to use the integral of our constant pressure specific heat from table A6, and this is only valid up to 1200 Kelvin. Lastly, we can use our published values from table A8, which is valid up to 3000 Kelvin. The only caveat is there are not many materials listed in table A8.